So let's continue our discussion of gases, liquids, and solids. We've done the phase diagram last time, and we talked about behavior of real gases. So today we're going to focus on the structure of solids. Okay, when we talk about the structure of a solid, okay, we're referring to how the particles are arranged in that solid. In other words, how the atoms or the ions or the molecules are arranged in that solid. You have what's called a crystalline solid if there is a long range order or if there's a repeating pattern in the way the particles are arranged. Okay, crystalline solids have the following characteristics. They tend to have smooth, flat surfaces when you cut them. Okay, you're familiar with crystals, right? And crystalline solids are in fact the most stable. Okay, so it's majority of naturally occurring solids are actually crystalline. So it's the most stable way that the particles can be arranged in a solid. Okay, so this is what you get if you give the particles, the atoms, the ions, or molecules that make up your solid, if you give them enough time to settle into their positions in the solid, the most stable arrangement that they will assume would be the one that leads to what we would call a crystal. Okay. Now, another type of structure where there's no repeating pattern is called amorphous. This is usually what you get if these particles don't get enough time to settle into the most stable position. So there's no repeating pattern. Although within an amorphous solid, you might have just regions within that amorphous solids that you might consider crystalline. Okay? So you can say you can have crystalline domains within an amorphous solid. All right. So the basic repeating pattern in a crystalline solid is what we would call a unit cell. Okay, and you can determine how these particles are arranged in your crystal. You can determine what's the unit cell experimentally using a technique known as X-ray diffraction. Okay, and the simplest we're going to talk today about the simplest type of unit cells where you have them arranged in cubes. The repeating pattern is cubic. Okay, so you have a simple cubic unit cell is one that looks like this. Okay, that's a unit cell. Notice you have a cube where at each of the 8 corners of the cube, you have 1, 2, 3, 4, 5, 6, 7, 8. You have an atom, a particle, or an ion at each of the 8 corners. Okay, and so this is what would this be? And that's several of those unit cells put together. Okay, there's a program that you can download from UCLA that we have here I have it on this computer that you can use to let me see, visualize these crystal structures. Oops. Okay, it's called crystalline solids. Okay, and so this is a cubic cell, so you can get a better visualization. Okay, so that's one simple cubic cell. You can see there is one atom at each of the 8 corners. All right, and if you want to show multiple cells, several of these cells together, then that's what you get right there. Okay. So, of course, there are really no rods linking those atoms together. They just, it looks like that. But the rod simply is a good way for you to visualize the three-dimensional structure. So you have an array of these atoms arranged in this repeating pattern. So that's called a unit cell. Okay. And you can have what is known as a body-centered cubic cell. In a body-centered cubic cell, you have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 atoms, one at each corner of the cube, but in the middle of the cube, you've got one extra atom. Okay? So effectively, how many atoms do you have in a cubic cell? In a simple cubic cell? Okay. You have to realize that each of these corner atoms is shared with how many other cells? Like this one right here, this is a corner atom, right? It's shared by how many cells? 4 on top, right? There's 1, there's 2, there's 3, right? And there's the fourth one on top. And there's 4 below, right? So it's being shared by 8 cells. So one atom in a simple cubic cell is actually shared by 8 cells. So effectively then, only 1/8 of an atom, you could say, belongs to a particular unit cell. So what's 1/8 of these 8 atoms? 1. So effectively you have one, you can say if you were counting atoms, each unit cell would account for effectively 1 atom. Okay? Now in a body-centered cubic, how many atoms effectively is contained in one cell, one unit cell? 2. 1/8 of the 8 plus the 1 that's in the middle. Okay? So this is what a body-centered cubic looks like. What if you have you can have what's also called a face-centered cubic. Look at what happens in the face-centered cubic here. At each of the 6 faces, 1, 2, 3, 4, 5, 6, you have an extra atom. Okay, let me see if I can make that visualization a little easier. Cubic, okay, this was the body-centered. Okay, this is your one cell. You got one in the middle. That's easy to visualize. But if you have face-centered, look at that. At each of the 6 faces, okay, so here's one face right here. Okay, this is one face, right? There's an atom on that face. So how many faces does a cube have? 6 faces. All right, so effectively, how many atoms belong to one cell if the structure is face-centered cubic? Okay. Each of these each of these atoms and the center of a face belongs to how many cells? Let's show multiple cells here. Okay. Let's see if we can visualize it better this way. Can you see that? Okay, let's look at this one right here. This is shared between this face right here is shared between 2 neighboring cells, right? So a cell on a face would be shared by 2 cells. So effectively, only half of that atom belongs to a cell. So if you have 6 faces, but only half of those 6 faces, only half of the atoms on those 6 faces belong to the cell, 6 divided by 2 would be 3. Plus 1/8 of the 8 cells in the corner, that gives you effectively how many atoms belonging to a face-centered cubic cell. Total of 4. Okay. So this is face-centered cubic. No. Okay. The face-centered, there's one on each face in the center of each face, but not one in the middle of the cube itself. Okay. So that's what you call a face-centered cubic crystalline structure. Okay, so how many particles are in a unit cell? Let's do a quick review. Is it A, 1, B, 2, C, 3, or D, 4? For a simple cubic cell, how many? Is it 1, 2, 3, or 4? Okay, that would be 1, right? 1/8 of the 8. What about a body-centered cubic? Is it 1, 2, 3, or 4? Okay, this is a body-centered cubic. So you have 1, 2, 3, 4, 5, 6, 7, 8. 1/8 of those is 1 plus the 1 in the middle. That's 2. So the answer is 2. Very good. And for the face-centered cubic down here, how many particles are in a unit cell? answer is 4. Very good. So that's 1/8 of the 8 corner atoms. That's 1. And then 1/2 of the 6 atoms that are on the center of the faces. That would be 3. 1 plus 3 would give you 4. Very good. Oops. Uh-oh. Oh, here's a freebie. Just click A. Click on the wrong button. On. Alright, so let's look at some applications of this. Okay, polonium is the only known element to actually have a simple cubic crystal structure. So it's got a simple cubic unit cell. The length of one side of the unit cell is 339 picometers. So the length of your cube is 339 picometers. What's a picometer? 1 picometer is 10 to the negative 12 meter. Okay? And there's no naturally occurring isotope of polonium, but the most stable radioisotope is polonium-209, which has a mass of 208.92 atomic mass units. So the molar mass is 208.98 grams per mole. Okay? You can actually calculate the density of a solid sample of polonium based on this information. How would you calculate the density? Well, what's the mass of one unit cell? 208.98 atomic mass units, but you have to change that to, let's change that to grams. So it's mass over volume, right? Effectively, one unit cell contains one atom, right? So what's the mass of one atom? 208.98 grams per mole. What's a mole of atoms? How many moles are there in one atom? I mean, how many atoms are there in a mole of atoms? 6.02 times 10 to the 23rd, okay? So that's the mass of one atom. Divided by what's the volume that would be effectively occupied by one atom? That accounts, what volume accounts for the presence of one atom? The volume of the cube. What's the volume of a cube? 339 cubed in this case, so A cubed, right? So the side is A, so it's A cubed, so 339 times 10 to the negative 12 meters cubed. And how much would that be? What's our density? Density would be, calculator, 208.98 divided by 6.02 times 10 to the 23rd divided by parenthesis 339 times 10 to the negative 12 close parenthesis. Okay, raised to the power. How do I raise things to the power on this calculator? Here, x to the y, raised to the power 3. So that is to 3 sig figs, 8.91. How many decimal places do I have here? 1, 2, 3, 4, 5, 6. So 8.91 times 10 to the 6 grams per cubic meter. How many grams per mil is that? Convert cubic meter to liters. Or you can just say cubic centimeter. What is 1 cubic centimeter? That's a milliliter, right? Here's a quick way to convert. 1 cubic centimeter, okay? 1 centimeter cube is equal to 1. What's a centi? Centi means 10 to the negative 2 or 0.01, right? So 10 to the negative 2 meters cubed. So 1 cubic centimeters is 10 to the negative 2 meters cubed. So that allows you to do your conversion quickly. Okay, oops. Let's put that aside. So that's how much? 8.91. Okay, 10 to the negative 2 cubed is 10 to the negative 6, right? 10 to the 6 times 10 to the negative 6 is 10 to the 0, so that's just 1. So this is grams, 8.91 grams per cubic centimeter. And of course, you know that 1 cubic centimeter is a milliliter, right? So it's 8.91 grams per mil. Okay. Packing efficiency, okay, refers to the volume of the spheres divided by the volume of the unit cell. If you were to assume, okay, that each particle is a sphere of the maximum possible size that could fit in a cell, okay? So you assume you have a unit cell. Imagine you have the maximum possible size spheres that you can fit in that unit cell, and they're all equal size. What we call the packing efficiency is the amount of space that's occupied by these spheres divided by the actual volume of your unit cell, okay? So, and you'll find that for a simple cubic cell, the packing efficiency is 52.3%. Why is that? Here's how we can figure that out. Imagine you have a cubic cell right here. You're looking at it from the top, right? So it's packed with spheres and they're as big as possible. So if the spheres are as big as possible, what happens? The radius of your sphere, of this sphere, plus the radius of the neighboring sphere together, 2r, that's going to be equal to the side of the cube, correct? So the length of the side of the cube is 2r. What would be your volume of the cube? It's going to be a cubed, right? And which is going to be equal to what? 2r cubed, correct? What would be the volume of a sphere? You remember the formula for the volume of a sphere? It's 4/3 pi r cubed. Okay, so that's the volume of one sphere. Why are we talking just one sphere? Effectively, what did we say? How many did we say? How many spheres would be in your simple cubic cell? It's just one atom, right? One sphere. So that's the volume of the sphere divided by the volume of the cube. What would that be? So volume of the sphere is 4/3 pi r cubed divided by the volume of the cube, which is a cubed, which is 2r cubed. That's your packing efficiency. And so what would that be? Your r cubed cancels out, right? So this is going to be 4/3 pi in the numerator divided by, okay, you got your r cubed there. And 2r cubed is 8r cubed. Okay, so r cubed cancels out. And that gives you 4/3 pi over 8. So let's simplify this. That's 1 and that's 2, right? So that's pi over 6. Correct? So what's pi over 6? Pi, where is pi over here? Let's just do 3.1416 divided by 6. It's 0.50, it's 50.524, okay? Oh, here's pi. Pi divided by 6 is 52.4, 0.524. Okay, so it's 52.4%. Make that correction. So this is going to be equal to 0.524. So you're looking at 52.4%. Right? So that's what you call the packing efficiency. What about if you're dealing with, okay, here's an example. Polonium. Okay, going back to polonium, what's the length of one side? We said was 335.9 picometers. Okay, let's figure out what's the size of a polonium atom is. Based on this information, if it's a cubic cell, okay, here's one polonium atom, here's the other polonium atom, simple cubic, and this is the radius, right? And that's the radius. This is center to center, right? So A, the side of the cube, we say is equal to 2r. So what's the radius of a polonium atom then? If you were to imagine that as the size, that's one way you can uh, determine the size of atoms, okay, based on crystal information. So what's the radius of your polonium atom? It's just going to be A over 2R, A over 2. What's our A? 335.9 picometers divided by 2, which gives us 167.95 picometers. So it's about 168.0 picometers if you do your sig figs, right? That's the radius of your polonium atom. What is the volume of your polonium atom? How much volume does it occupy? 4/3 pi r cubed. So 4/3 times pi times 168.0 times 10 to the negative 12 meters cubed. Okay? What's the packing efficiency? Actually, we don't have to calculate packing efficiency. We should already know what it is, right? It's 52.3%, right? 52.4%. Okay. And so if you did calculate your volume, you'll find it's 1.984 times 10 to the negative 29 cubic meters. All right. What if you have a body-centered cubic? What's your packing efficiency? If you did this, you'll find that the packing efficiency is 68%. Why is that? Imagine this, remember you have an atom in the middle here, right? And you've got an atom at each corner, right? So you got these three atoms. So this is the atom in the center, okay? And this is in the corner. And this is at the corner. Okay? Using Pythagorean theorem, okay? If this side here is A and this side here is A squared plus A squared would give you the hypotenuse squared, right? So A squared plus A squared equals what? The length of this diagonal, right? So it's going to be 2A squared. So this thing right here then is square root of 2 times A. So this length right here, square root of 2 times A. A squared plus A squared is equal to 2A squared. And then if you use this one right here, look at this right triangle right here. This is square root of 2 over A. This is A. The square root of 2A. I'm sorry. And so this length right here, the diagonal across the cube would have a length of square root of 3A. Okay? So that means that, let's look at the length of the diagonal. You have 3 atoms across the diagonal, right? So this is one corner and this is the other corner. Well, that's the radius of one atom. That's the radius of the second atom. That's the radius of the second atom. That's the radius of the third atom. So that's 4r right there across the diagonal. So that 4r is square root of 3a. Okay, this is square root of 3 times a. So 4r is square root of 3 times a. So what is a? Solve for a. A is equal to 4r over square root of 3. Okay, so how do we determine the packing efficiency? The volume of the cube divided by, the volume of the sphere divided by the volume of the cube. But how many spheres do we have in a body-centered cubic? 2. 1/8 of the 8 corners, right? Plus the one in the middle. So your packing efficiency is the volume of 2 spheres. So 2 times pi, what's the volume of a sphere? 4/3 pi r cubed divided by, what's the volume of the sphere? A cubed, which is 4r over square root of 3 So your packing efficiency is how much? That's going to be 2 times 4, so that's 8. 8 pi over 3 in the numerator times r cubed. In the denominator, you're going to have, what's 4 cubed? 4 times 4 times 4, 64. 64 r cubed over, what is square root of 3 cubed? Square root of 3 cubed. And that's square root of 3 times square root of 3 times square root of 3. That's square root of 3 times square root of 3, right? And so cancel your r cubed, and let's see if we get 68%. That's going to be what? 8 pi over, okay, times 3 square root of 3 over 3 times 64, right? Is that correct? So 3 cancels out, 8 and 64, that leaves you with 8. So that's square root of 3 times pi over 8. So pi times square root of 3. What's the square root of 3? Raised to the power 2 divided by 8. 68%, 0.68. Okay? So you're looking at 68% packing efficiency. In other words, you get more, okay? More of that volume of the cube is occupied by the particles of your solid. Whereas in a simple cubic, what was our packing efficiency, you remember? 52%, this one is 68%. Alright, what if you have a face-centered cubic? Well, you have to, what you need to do now is you can say this, there's 1, 2, 3 across the face, right? 3 atoms touching each other across the diagonal of a face. So this 4R, so you have 3 atoms. So that's R for the first atom, R for the second atom, R for the third atom, R for the fourth atom. So that 4R must be equal to square root of 2 times A. Okay, so for the diagonal of a face, this is A, that's A, so this must be square root of 2A. So that means R is equal to 4R. The length of the diagonal of a face is equal to square root of 2 times A. So you can say that A is equal to 4R over square root of 2. Okay? And how many particles are in your face-centered cubic? 4. Half of the 6 face particles would be 3 plus 1/8 of the 8 corner particles would be 1. 3 plus 4. So your packing efficiency is going to be equal to what? 4 times the volume of a sphere, which is 4/3 pi r cubed. Okay? And then your volume of a cube is 4R over square root of 2 cubed. And you should be able to show that this comes out to how many percent? 74.5%. Okay, so this is a much tighter packing of the particles within your unit cell. Okay, let's look at an example here. The unit cell for copper metal is face-centered cubic. Okay, so how many particles per unit cell? Face-centered cubic? 4. Okay. The density is given as, you can find this experimentally to be 8.92 grams per mil. So that's 8.92 grams per cubic centimeter. Figure out the length of one side of a unit cell of copper and then calculate the radius of a copper atom. So how are we going to do this? Let's assume you have a mole of atoms. What's the mass of 1 mole of copper? Molar mass of copper, you look it up. 63.5, 55 grams. Okay. What would be the volume of a mole of copper then? The density is 8.92 grams per mil. So the volume is mass over density, right? So 63.55 grams divided by 8.92 grams per mil. That would be how much? 7.12 mils. Okay. So that's 7 point, see? What was it? 7.124 mils. I'm going to put an extra sig fig there, an extra digit past the last sig fig there. So 7.124 milliliters. Okay. So this is 7.124 milliliters. Keeping in mind I only have 3 sig figs. Since there are 4 atoms in each unit cell, how many unit cells would you have? You have a mole of atoms. Okay. Every unit cell will be able to hold 4 of those atoms. So how many unit cells would you have total? Okay, you've got 16 people. Each bedroom can accommodate 4 people. How many bedrooms do you have? So how did you get 4? 16 divided by 4. So how many atoms do we have? Avogadro number, right? Divided by 4. Why 4? That's a face-centered cubic, okay? Face-centered cubic, you can put 4 atoms in a cell. So that's going to be 6.022 times 10 to the 23rd divided by 4. That's the number of cells that you have. Okay? So what's the volume of a unit cell? You have the total volume, you have the number of unit cells. You just divide the number of cells by, you divide the total volume by the number of unit cells. That gives you the volume per cell. So what's the total volume? 7.124 milliliters divided by the number of unit cells, which is 6.022 times 10 to the 23rd over 4 cells, right? So that's the volume of each unit cell. What would that be? .124 divided by 6.022 times 4. It's 4.7 times 10 to the negative 23. Let me try that again. 7.124 milliliters divided by 6.02 times 10 to the 23rd. Let's make it this way. Times 4. So 4.73 times 10 to the negative third. 4.734. 3 sig figs times 10 to the negative 23rd milliliter. What's a milliliter? That's a cubic centimeter, right? So if that is the volume of your cubic cell, your unit cell, that's 4.734 times 10 to the negative 23rd cubic centimeter. How is that related to the length of the side of the cube? What's the volume of a cube if the length of the side is A? That's just A cubed, right? So how long is the length of the side? How long is the side of a cube? A would be equal to cube root of 4.734 times 10 to the negative 23rd cubic centimeters. And that would be equal to, let's see, raised to the power cube root. So here, I just take the cube root. That's 3.62617 times 10 to the negative 8. 3 sig figs centimeters. Okay? Is that what we got? Oh, I don't have that answer up there, but I have the final answer is 127.8 picometers is the radius. Okay, so that's the length of the side of a cube. What's the radius? Face-centered cubic, you remember? That's across there, that's 4 times the radius, right? 4 times the radius is equal to square root of 2a. Correct? Remember? Face-centered cubic. 4 times the radius is square root of 2a. It's face diagonal. So 4r is square root of 2a. So what's our radius? Square root of 2a over 4. Okay. Square root of 2 over 4 times 3.617 times 10 to the negative 8 centimeters. That gives you, okay, let's see. Okay, so we have our centimeters times square root of 2 times 2. That's odd. There's no square root symbol here. Raised to the power 2. That's square root of 2. Raised to the power 1/2. Divided by 4. 1.27. Okay, or 1.28. 3 sig figs now. Times 10 to the negative 8 centimeters. Okay? Yeah. So what would that be in picometers? That's 1.28 times 10 to the negative 8. Centi means what? 10 to the negative 2. All right? So that's going to be 1.28 times 10 to the negative 10 meters. Okay? And 10 to the negative 10 meters is called an angstrom. Okay? So this is 10 to the negative 10 meters. So that's 1.28 angstroms. Typically, when you're solving problems like this, typical interatomic distances in atoms would be anywhere between 1 to 2 angstroms. Okay? So if you're getting a number that's way off from that, 1 to 2 angstroms, that's telling you you probably made a mistake somewhere. Okay, so it's a good thing to remember, especially if you're taking a multiple choice test. Okay, so but you should be getting somewhere close to between anywhere 1 to 2 angstroms, typical distance between atoms in a solid. Okay, now what is that in picometers? That's 1.28 times 10 to the negative 10 meters. So how do I change meters to picometers? 1 picometer is 10 to the negative 12 meters. So to go from angstroms to picometers, effectively you just multiply by 100. That's 128 picometers. Okay, so that would be the radius of your copper atom. Okay, 127.8. All right. Some examples of crystalline solids, you can classify them into different types. You can have ionic solids, okay, ionic crystalline solids. They're characterized by very high melting point because of ionic bonding. They're also very brittle because what happens is this. In your crystalline solid, okay, you got pluses and positive ions and negative ions right next to each other, right? If you hammer, okay, if you hit, let's say, a solid, an ionic crystal by a hammer, what happens is you shift these. Let's say you were to shift this just a little bit to the right because of the force from the hammer. What happens? These negative ions could be temporarily be right next to each other, and your positive ions would be temporarily right next to each other. So that would trigger a very, very strong repulsion, and so that breaks apart your crystal. So the brittleness of ionic compounds is due to the strong interionic repulsions that would be triggered by the slight displacements that would occur if you were to hit it with a hammer. Okay? Now, molecular crystals, you can have molecules settle into a nice repeating pattern into a crystal. But generally, these crystals would have low melting point, and they have a tendency to just sublime. Okay? And the reason for that is the forces that are holding those molecules in your crystals are relatively much weaker than the forces holding the ions. You have what types of forces hold molecules together in general? Intermolecular forces. So the most common one would be London dispersion forces. Those are relatively weaker compared to the ionic bonds that hold ions together. You can also have what are known as non-bonding atomic crystals. Generally, when you're dealing with noble gases at very low temperature, okay, your atoms of your noble gases are just held by very, very weak London dispersion forces. So you can have them settle into a crystal at very low temperature. So it's just a collection of atoms in a solid. That would be what you would call a non-bonding atomic crystal. You can also have metallic crystals. So metals and form metallic crystals. They have a very high melting point because of metallic bonding. What's metallic bonding? You have your nuclei, okay, of your metal. Imagine it as being buried in a sea of electrons. Okay, in a metal, remember from your periodic trends of atomic properties, your metals have very low ionization energy. Right? They don't hold on to their electrons very well. Electrons in a metal are very loosely held, so you can imagine in a metallic solid, you have these nuclei of your metals surrounded by a sea of electrons, buried in a sea of electrons that are very easily moved, that can move very easily. So that's one reason metals are good electrical conductor. Okay, so the malleability and ductility of metals has to do with the fact that atoms, the movement of your atoms, when your nuclei in your metal move, the bonds don't get broken because it's really the metallic bond is just delocalized over the entire structure. Okay, so what does malleable mean? What's a mallet? It's a hammer, right? Malleable means you can hammer them into thin sheets, so you can easily move those metal atoms so that you can spread them out into a thin sheet. Ductile means you can draw them out into a thin wire. So copper metal, you use that for your electrical wires. So your electrical wires are made up of metal, copper metal, right? Ductile means can be easily drawn out into a thin wire. Malleable means you can hammer them into thin sheets. The opposite of those things would be brittle, right? If you hammer like a salt, what happens to a salt when you hammer it? It falls apart. It's brittle. Okay. So, but you can make your metals hard and brittle by introducing irregularities within the structure, within the crystal structure. And you can do that if you were to cool your metal and then you hit it with a hammer, okay? Or you can mix different kinds of metals. So you disrupt the order in the crystalline structure. You can make your metal brittle, okay? Now, heating, if you were to heat a metal, it has a tendency to soften. Why? Because by heating it, you're giving the atoms of the metal the ability to move about. What's the word for it? You give them time to settle into a much better position in a way. Okay, so that's a way of removing irregularities. You can also have what are known as covalent network covalent crystals. These are crystals that are formed by atoms that form covalent bonds. So examples of these would be, the most common one would be diamond, graphene, and graphite. Let me see if I can pick up some structures from the pictures from the web for diamond crystal. Okay, let's search for images. Okay, so Here's a picture of a diamond, okay, crystal. So you can see each carbon is a tetrahedral center. It's moving. All right. Each carbon is a tetrahedral center. It's covalently bonded to 4 other carbon atoms. So it's a very, very strong structure. Okay. Diamonds are one of the hardest materials known. It is the hardest material known, right? And you can also have graphite. Okay. You can see all the atoms are covalently bonded. Okay. Graphite is, you can think of graphite as actually sheets of a molecule called graphene. In graphene, you have sp2 hybridized carbon. Okay. So each of these atoms here that are arranged in a hexagon are sp2 hybridized carbon atoms. So a sheet of carbon atoms forming these hexagons here is what you would call graphene. Okay. And that you have layers of those to form graphite. Okay. And where do you find graphite? The lead of your pencil. Okay. So those sheets of carbon atoms would just slide off your pencil and attach onto your paper. Right? All right. So those are some types of crystalline solids. What about amorphous solids? Typically, the amorphous solids you find are made up of very large molecules, polymers, so they have a hard time to set up a regular arrangement. Okay, so naturally occurring large molecules, examples of those are proteins and carbohydrates. You can have synthetic, that means man-made, okay, substances that are amorphous, solids that are amorphous. We call them plastics. Okay. Your common everyday glass that you drink from, okay, that's an amorphous solid. Okay, they're made up of small, it's made from molten sodium carbonate and sand. So you've got sodium ions, carbonate ions, sand is silicon dioxide. Okay, it's cooled quickly. It's rapidly cooled. It's molten and then rapidly cooled. Because it's rapidly cooled, your particles don't have enough time to settle into a nice regular arrangement, so you don't get crystals. You get a glass. That's what a glass is. Okay, it's an amorphous solid. And so that's the end of this lesson on solids and liquids and gases.